Okay, so welcome to the coding section. So I made a folder called Transformers Video, and first of all, what we're going to do is actually make our embedding.py, and this is what I just said, which was embedding.py. And embedding, as you remember, actually requires not much, and the most, let's say, complicated part would be actually the positional encoding. So first of all, we're going to actually make two classes. First class will be NumPy embedding, and the second class will be embedding. And the difference is that the weights and also the positional encoding. For embedding, we're going to have the positional encoding there, and for NumPy embedding, we're going to have those self-dot weights for each of the tokens. So, as you learn, these usually require a initialization, so that's more easy to work with when you're using it in other files. Yeah, so our initialization is going to require a vocab size and embedding dim. This is actually going to be used in our embedding, so we're actually not going to be. So let's just initialize our weights. Now I don't have the notes pulled up, but as I remember, and as you remember, we have the vocab size and the embedding dim. And we're just going to times 0.1, such that it's smaller and doesn't set anything up. And we're going to have none. And then the embedding dim, as you remember, is 64. So each self-dot weight will be a vocab size and embedding dim 64 matrix. So we can do that. So we're going to call a forward dot function, and the forwards basically mean, because we're talking about forward pass, so this is only the forward. I'm not going to code the backward yet, and this is the forward of the NumPy embedding dim class. So we're going to have the input, which is our tokens, and now our tokens will grab these weights. And we're just going to make it into a NumPy array, such that we can map it. And then we're going to return our self.weights, weight of dot inputs. And all this does is basically, we're just going to index our corresponding tokens to its own vector. And same thing goes for embedding. Since this is the guy that is going to be calling NumPy embedding, we're going to have a bit more requirements at the first. Vocab size and our max sec length, which, as you know, is going to be longer than sec length or shorter. And self.word embeddings is, we're just calling the class. There's thunderstorm. NumPy embedding, vocab size, as we just mentioned, and max sec length. Cool. Call the self.pe, even though we don't have it yet, but just know that we're going to make it soon. And then max sec length, and then the D model. So later on we're going to make this. And then now we're going to make it def positional embedding, and call self max sec length D model. Cool. And PE equals to np.zeros, because we're making a matrix and we're adding it, remember? So we're just doing this. We're making a data frame. Now position will be equals to np.arrange. So this is actually taking what we learned and we're making it vectorized so that it's all faster and we don't have to call it for a for loop, which would be disastrous if we are trying to actually use it for big terms. And range 0 d model 2 times negative np dot log 1000.1 over d model. In this code, actually, in our discussion just now, we did not talk about how we do this div term, but sorry, this is actually using the identity with e. So let me just type it here. E to the power of ln x equals to just x, and we're just doing that for e to the power of our negative, remember the ln, so our 10,000 times I over d model, which is the same div term that we had in our actual, so it's the same div term that we had in our positional encoding. It's just that we're applying to this, which is basically the same thing. And then now we're applying this because we want it to apply for even when it's sine, well, sine when it's even, and odd when it cos when it's odd. So np dot sine position times div term. So now, since we made the div term this way, we can actually put it, just times it. We don't have to actually put it under, which is good. And the p 0, 1, 2. So it goes 1, 3, 5 with, difference of 2. Cos. Yep, then that's good. And we're going to return our PE because we're not actually adding it here. We're just going to add it in the forward. Word embeddings self word embeddings dot forward and inputs, which we just made, right? Yes, we have just made. Yeah, and we're going to return the word embeddings plus the self.pe. Yeah, and then we're going to add the one we made, which is this. I'm going to add this like this. Yes, actually this part is just making sure that we add it according to how long it is, so we don't add it more than we need to, which is good. And now after we're done with NumPy embedding, let us just make a new block called attention.py. Now same thing again, import pandas as PD, import NumPy as handp. It's going to happen for everything. Attention, cool, def, init, self, d, model, num of head, which we equals to 4, so we preset it, so we don't have to tinker with that. Equals 100. We're just going to do that because we don't want it to be too long. And this is all we need. So we have these presets parameters that you can tinker on with yourself if you need to. Oh, sorry. There should be actually heads instead, yes. And the D model. So this double split is actually for, I think, yes, integers. So I think it rounds up, if I'm correct. But in this case, it doesn't matter for us because we're actually going to find a number of heads, which makes D model divisible by 4. In this case, 4, yeah. As I said just now, these actually are D model squared size, and we're just going to do that for everything. Let me just copy it later. Random D model times 0.01, and we have to do this 2 more times for our value and output that concatenates our outputs later on. Whoa, what happened? Yep. And then self.casual mask, which you just learned, is actually the np.triu, the upper triangle of np.ones. This doesn't really matter. Well, it does. I mean, they just times each entry by itself, corresponding entry, such that, so it's 0. So if it's 1, they don't change at all. But if it's negative infinity, then bye-bye. And that's what we want to do to useless and left flow data, such that the guy doesn't really cheat. And that's a really important thing in machine learning, such that we don't overfit and our data can actually learn from experience rather than just cheat and just copy everything. Def forward. Now, there will be some procedures here which doesn't really make sense because we're actually saving some of our data for later, because in our backward pass, backward propagation, we actually need some of the data to do math derivations for the chain rule. So if you see me actually saving some of the stuff that we don't actually use, just know that it's probably going to be for our propagation. So we save these 2 sizes for batch size and sequence length because that's what the X shape is. I can't really show you what the X shape is right now because, well, I haven't loaded X, but I mean, just now we talked about how X actually looks like, which is batch size, sequence length, and our D model. So that's basically what it is right now. Batch, sec, D model. Just keep in mind because it's going to be very messy later on if you don't remember. See, I already saved it once here. And this is our pattern mask. It's a true and false matrix where token of IDs is not equal to 0. So that means the pad is actually 0, and if pad, then false. If not pad, then true. So we can use that mask for later on. Sorry. And then now we have to make our queues. So we do have our wait queues, wait queries, but we don't have the big queries where we already matmul X. But now we matmul X. And we matmul K. Same thing goes for V. Now we do a bunch of reshaping. So this is the part where single head attention and multi-head attention actually differ, is that we actually reshape our data to this, which is the batch size, sequence length, number of heads, and heading dim, and then transpose 2, 1, 3. This is actually to help with later on when we do our scale dot product attention. It is kind of technical, and you're going to have to look at it a bit further yourself to be able to understand, why we do such things. But if you're enough of a veteran in linear algebra, it's actually not that hard once you understand what's going on. But basically, you're not changing the batch size, right? The batch size is going to stay there. And then you're just going to switch 2 parts, which is the sequence length and the number of heads. So you're going to switch that such that, later on we can make it sequence length and sequence length. And we're saving it again because we need it later on. And it's just going to make the next video a bit more simpler. Oh, sorry. V heads? V. And yeah, now the attention output actually equals to self dot underscore scaled underscore dot underscore product attention. This is what we learned just now. The QKT over root D cube, DK softmax matmo V. Now, if you don't fully remember, I recommend you just go back and check it out yourself before coming back and continuing. Yep, so we have our output, and then let's say that we assume that we already have it, and we just reshape it to batch size, sec length, self.d model. Now, I'm a bit more fluent in how I make it because I made it a bunch of times, and if you haven't, it's going to be a bit hard to remember the steps and how the shapes work. So this is a good way to kind of see how it's coded, and self dot weight underscore O, correct. And now it's like recursion. I mean, we made it before we used it, but here product attention self QKV pad mask. Oh, sorry, pad mask scores equals to Q at K dot transpose 0, 1, 3, 2 root NP dot square root DK, which is D model. Sorry. In this case, wait, I have to clarify. In this case, actually, D model will be the self-head dim because we're actually doing it with a multi-head attention. So we're not actually over D dim, D model, but actually D head. Scores plus, so this is actually the casual mask, well, what we just made, right? And then we're just going to add that, a bit more different things. We're going to do this because it's actually, right, because right now the scores, they're still into heads, right? This is actually such that it matches the sequence length. Now this sounds kind of weird because I mean we just literally padded it down. We're going to pad it down during the testing. So if you ask why, well, why do we need to do this to make sure that they match the sequence length? Well, it's because we're just making sure that if during inference that it's a lot shorter, and it's just defensive coding. So there's less bugs and there's less issues that can occur because anything that can go wrong will go wrong. So we're just going to make sure that's like that. And then for this, we're just going to make a new axis so that we can add it later on because they don't match in dimension. And scores equals to np.where pad mask scores negative np.infinity. So this is, since the pad mask is a true and false matrix, the parts where it's true, we just have it scores. The parts where it's false, negative dot infinity, so that we don't apply any attention onto it, which is nice. And then we have our attention weights, self.softmax. We're going to build that because you don't want to kind of interrupt what you're doing, right? You just want to go in the flow. And then as long as you remember the procedure, it shouldn't be too hard. Here we're saving the tension weights again. Here as well, because we need it. Okay, we need it when we backward propagate weights at V. We already have V, so we just add it. Self-explanatory. We talked about it already. And then, X can be anything, can be vector, whatever. And then what we're doing here is actually normalizing it. So we're just finding the max. So let's say we put it infinity, and infinity means we don't want to deal with it. And if we don't want to deal with it, and it is the max, so let's say negative infinity, right? We don't want to deal with negative infinity. And if the max is negative infinity, that means the entire row is negative infinity, and means the entire row should not be calculated. And the entire row is wrong, and we don't need it. That's basically it. And that is why we're doing this. Is so if the max of the vector is negative infinity, then we set everything to 0. Otherwise, we have x minus x underscore max to normalize it. And then our x will become equals to, as we just saw, so everything is not exponential. And then the denom will equals to the sum of it, because that's the entire thing we just talked about. And then the denom goes to np.where denom equals to 0, because we don't want, remember, we don't want any exploding things. Return x over denom, because denom for everything will be the same. So that basically covers everything about attention, which is good. Layer norm. Same thing, it's a routine now. Because, I mean, we're building the entire thing from scratch. We're not going to have anything fancy like torches or anything like that. Oh, sorry. A space, self, the model. That's going to be our initialization parameter, because everything else doesn't really matter. Well, it all depends on the model, so it doesn't really matter. And then self dot gamma dot ones. This is so that it doesn't become 0 at first, which is weird. It just becomes, everything is the same as it came out. So we can start at default and let the model decide whether it needs to unnormalize or do something weird with it. Now, just now we already finished attention, so this is a lot more, it's going to be a lot more easier. This is just the np.mean. And you see me all do axis equals -1. It just means the last axis. So it's going to be the mean for that row, because that's the sequence. np not var x-axis equals -1, and then keep them true. Keep them true is actually just a way to keep the dimensions the same, because sometimes if you don't, all sorts of bugs come out, and the best way to not deal with bugs is to just kill them in the first place. And this is what we already talked about, is the VR plus 1e -5, which is the epsilon. We don't have a variable for it because it's kind of redundant. And we just save it for backwards later. And this is what we already talked about, where we have a gamma times the norm plus the beta. And that is layer norm 1 and layer norm 2. And then neural network. I'm going to call it twice, so there will be actually 2 gammas and 2 betas. Just something to know about. Because if you had the same for both, probably a disaster. Yep. And you remember what FFN is, right? So it just projects higher, higher dim, non-linearity, lower dim, done. Really simple. I mean, the whole project, like, the hardest part was going to be attention. We all knew that. And today, we're actually not going to have a good output because we're just testing it. And a good output, or a somewhat good output, would not be possible unless you finish backpropagation and have good data. Same thing again, random. Now random is actually, if you don't know yet, is randomizing between 0 and 0.1. Yeah, 0 and 1. So it's going to have stuff like 0.1, 0.2, all the real numbers in between. Just something for thought. And going to, of course, initialize the biases as, well, not biases, but the B's with intercepts as zeros, so they don't have an effect at start. If you remember linear algebra, then you would understand why the process, why the sequence of D model, DFF, and DFF, and D model is different. And if you don't, you can take a class or just search it up online, because I'm here to teach about how to make a transformer from scratch. The forward, well, it's basically, so the reason why we do it in different sequences, just for your information, is just going to be like m and n. Let's say mn is the dimension, m rows and n columns, times nm is actually going to be mm. So that's why we have d model times df, f being d underscore ff, will be equals to df, and then you times fd, which is dd, and they just basically go back to where it came from, but now with more information and more concise information. So here we also have to save it because we're going to need it later. And just like in the neural network, we're going to say z1, z2, etc. Self.b1 and self.z1, oh sorry, self.z1, we're actually going to save it down, because this is actually really important later on, as we need to perform backpropagation, and this is literally ReLU. So if it's lower, 0. If it's higher, Z1. And then the non-linearity of these functions actually just help with adding complexity to the model. I think this code is kind of self-explanatory. You're just doing a NP dot product with these self weights and add the self biases, the intercept, sorry. And then you just save it down. Cool. So here's the guy who actually uses what we made. Oh yeah, and also, if you're making this in a web, let's say Google Colab or Kaggle, then some of the code here would be actually an error for you, because like here, let's say I'm going to import attention, like my guy here, right, like over here, this file, from attention, the file, I'm going to actually import attention, the class. Now, if you're in Kaggle or Colab, you're not going to need these 3 lines because it's already in the same file, and if you're just trying to import it, it's going to be like, hey, there's no file, and you're going to have an error. Now we just made these classes, and then as I said before, we're going to make 2 classes. First of all, the transformer block, and then the class of transformers. And then first of all, for transformer block, we're assuming once, right? So there's no for loop here yet. So this is going to be actually activated by our transformer class. And then we're just going to call and activate these functions, or these classes, sorry. And then the L1 and L2, you can see now it actually takes effect. We're activating the class twice. And then we have, yeah, that's it. Okay. And then forward. Now this is actually an excellent kind of preview of how it works. Now, if you don't remember, you can go back a bit. Actually, the attention going to need our token IDs, and we already have our token IDs from later when we called this forward in our class transformers. So you just kind of have to remember which class needs what kind of preset parameters. So for this, as I just showed just now, you need token IDs. And explicit attention output. So this is residual connection. And then you have the x equals x, sorry, self dot L11 dot forward. And remember, we just made it so it's just x. Same thing. And you just need x. X dot self dot L12. Cool. So now we're done with transformer blocks. We're going to go with our class of transformers. So it's basically the guy that conducts the entire symphony, the conductor, if you will. A lot of preset lengths and stuff, but to make basically a list of transformers. Transformer block D model num heads DFF max sec length for underscore in now the output prod is a matrix that projects it to the vocab size, so we can make a softmax function, and with the highest probability as the predicted variable. There's also something that was not mentioned in the math section just now, but also something that just comes in intuitively. So there's no need for forward. Just keep doing it again and again. That is done. Finally, we get to our last part. And before I start the testing part, I am just going to import a dataset, the random English sentences dataset, which is around 1,000. Yes, 1,000 random English sentences. And then, well, I think I got that. Yeah, I got that at Kaggle. So now this is not training, so there is no loss derivation, entropy loss, and stuff. We have, let me just take the name so I don't have to type it all out. And we're also stripping everything to the base form, so we don't have to deal with any weird symbols. And of course, we don't have because right now, what I'm going to say, in embedding, you don't actually take the alphabet and apply the token vector. You actually take numbers and apply the token vector. So this is the part where you turn the characters into number vectors, so that we can apply a append function to it. This is really tiring. All this does is make sure that everything is from 1 to 26. It's just defensive coding, same thing. Sometimes code doesn't make sense because it's already accounted for, but it's just a good way to make sure that we don't mess up, because there's no harm in being more careful. And we're just saying that space is character 27 and 0 will be our pads. Vectors equals to sentence to vex, right? And then we have s in it for s in sentences, so it's still a list. Max length, we set it to 100, just prefix. And now we're doing the padding. So remember, we didn't do the padding in embeddings, instead we got to do it here. So we're saying here, if the max length, well, the length of the vector is longer than the max length, we split it. So if the max length is 3 and your sentence is like, I went to the beach today because blah, 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 then it's just going to become I went to the, which doesn't make sense. But when you have a max length of 100, it's okay. Now that's why I chose that data set, because its sentences weren't that long, so we can still get good content. Now we have the paddeds, but we need the token IDs. We get an NP array. Now these are just presets. You can fiddle them as you like, but make sure that you don't explode your computer. These are what I usually use, and well, not what I usually use, but it's very computationally efficient for a test. Anything with more than this, or even a bigger data set, like 1,000,000, then you either do it in Causal with I think GPU P100 or GPU T4 times 2, or just don't do it, because I mean, you already have DeepSeek, you already have GPT and Claude. There's no reason for you to try and make one yourself, because it's going to require a lot of data, and this is not state of the art. This is not the top of current technology, but it is also a good transformer. Did I write transformer wrong? Transformers, oh shit. Yep. Flow. Made transformers well. Okay. Wow. If you watch back in the embeddings, this is actually what we're having to initialize with, and I'm just writing that in. So in transformer, which we'll call this. Sorry, I'm using the wrong brackets. And then this is the general function. Just reassuring. 7, 4. So what we're doing is we're actually starting with tokens equals to 27. So we're letting it freestyle basically. We're just doing one inference so we can see what it actually comes up with. But this inference is actually not going to be trained at all, so it's going to output gibberish. But if it outputs gibberish, you're probably halfway there. And this is what inference usually does. You padded it, and then you put it in the embedding. You take the logits after forwarding the transformer. Word X and padded, and it'll do everything for you. To logits, since we have actually since we actually have multiple transformers, we're making sure that we take the last logits, and not the ones in between. So that's why we do that. And this is just basically what we learned. It is the softmax function. And the softmax function is basically how likely it is to be A, how likely it is to be B. And just divide it. This is a good way. It's just the same as negative equal or plus equal. So it's just a little step, like an update step. So it's randomly choosing one of these given the probability it is. So even though, let's say A has a higher chance than B, it might choose B because it's random and we don't want a greedy split. Instead, we're making sure that there's variety, and if I ask it the same question, it's not going to answer the same every time. And if it's the next token is 0, which means it's pad, it's going to just stop immediately. And then the next token is just basically the list of our tokens, our return tokens. And this is basically reconstructing the sentence so that we can, as humans, read it. And if I have not done anything wrong and written everything correctly, without anything weird, we'll be able to hopefully have this work. Please. Alright. Okay. Okay, so back after changing some stuff. First of all, we have the unmatched quotation. If you catch this, then congrats to you. But yeah, and then you have to put the quotations here. The arrange should be actually 1R. I keep forgetting that always. And change all that. And then next, you have this one where it's not actually matching the dimensions. And then I was thinking, why was that? And I checked after, and actually, I think over here I wrote max sequence length when it should be D model. So forgive me for that. Yeah, and then also in the FFN, I wrote lower x rather than capital X. And here there was 0 because I forgot, and I, instead of this, where it should repeat everything else, I actually only did the space, which means it will output nothing. But here, finally, when you press, you see output something, and then there's a pad out here, and then it just stops. Now this is fully gibberish, but if you do backprop and you do have somewhat good data, it can give okay results. I have one that gave a few English words actually. So yeah, that's the end of the Transformers video. Pretty tiring, but it's a good build. And I'll upload a video on the backpropagation. I think I'll do it maybe separately. Yeah. Maybe separate on math and the code because it just takes a long time, mostly math. So yeah, thank you for watching.